Hello. In this module, we will learn the concepts of joint and conditional events and the corresponding probabilities. And we'll also learn the notion of independent events and how they are different from mutually exclusive or disjoint events. Let us first understand the terms joint events and conditional events. Joint events are those which occur simultaneously. Whereas conditional events imply the occurrence of one event given that some other event has occurred. Notationally, if A and B are joint events, they are written as A intersection B. That is, A intersection B denotes the joint events A and B, whereas if there is an event A which occurs when it is known that some other event B has already occurred, then the corresponding conditional events are written as A given B. This vertical bar denotes the condition and is read given that. A given that B has occurred, or A given B. The corresponding probabilities are called joint probability and conditional probabilities, and they are related as follows. The conditional probability of A given B is defined as the joint probability of A and B divided by the probability of B. Certainly, the probability of B must not be 0 because we cannot divide by 0. This symbol that we have used here is the triangle equality, and it is used whenever a mathematical expression is defined. Let us now take an example to clearly understand the notions of joint and conditional events and the corresponding probabilities. So let us consider rolling of a die experiment. Of a die, we assume die is a fair die, unbiased die. A die consists of 6 faces, and each face has certain number of dots from 1 to 6. So clearly the sample space for the die experiment is the numbers from 1 to 6. 1, 2, 3, 4, 5 and 6. Now let us define two events on this sample space. Event A is, say, the number of dots that show up is an even number. So even number for short. The corresponding sample points in event A will be 2, 4 and 6. And define event B as the number of dots which is less than or equal to 4. That means the corresponding event B will contain points 1, 2, 3 and 4. Now we are interested in defining the joint events A intersection B and the conditional events A given B. Let us first look at the joint event A intersection B. A intersection B means the event that the number that shows up is an even number which is less than 4. So it is the intersection of events A and B, and clearly it is two sample points 2 and 4, the intersection of A and B. Let us compute the corresponding probability, joint probability, probability of A intersection B, and that can be easily given as the number of points in the event A intersection B upon the number of sample points, or using the cardinality notation we can write probability of A intersection B is the cardinality of A intersection B upon the cardinality of the sample space. Cardinality simply implies the number of points in the given set, so which is equal to 2 upon 6, which is 1 by 3. So the joint probability in this case comes out to be 1 by 3. Now let us look at the conditional event A given B. Let us look at the conditional event A given B. Now what does it imply? A given B means the event, it is known that the number that shows up is a number which is less than or equal to 4. That means the event B has already occurred, and we are interested in finding out whether the number is an even number. So clearly the corresponding conditional event contains two sample points 2 and 4. The corresponding probability A given B is the number of points in the event A given B, which is 2 upon the number of points in the sample space. Now the sample space has reduced to B because B has already occurred. So the number of sample points is now 4, which is equal to half. So the conditional probability here is half, whereas the joint probability was 1 by 3. Clearly these two are not equal. Here we have computed the joint probability directly by counting the number of points in the joint event and the corresponding reduced sample space. Let us also verify this relation that we have just seen between the conditional probability and the joint probability. So let us verify the definition. So using the definition, we write probability of A given B is equal to the conditional probability, joint probability of A and B upon probability of B, which is equal to the joint probability of A and B we already computed is 1 by 3 upon the probability of B. Now what is probability of B? As it is clear from here, the number of sample points in event B are 4 and the number of sample points in the certain event sample space omega are 6. So the probability of B is 4 by 6, which is equal to 1 by 3 into 6 by 4, which is 2 by 4, which is equal to half. So which is same, as you can see that the probability that we directly computed and that we computed using the definition are same, which has to be the case. Let us now look at the other aspect where the occurrence of event B has no effect on the occurrence of event A. That means the probability of A given B is same as probability of A. In that case, we say that event A and B are independent events. Using this and the definition of conditional probability, one can write probability of A given B, which is equal to probability of A intersection B upon probability of B, which implies probability of A intersection B equal to probability of A given B into probability of B. Now if A and B are independent, then probability of A given B is simply probability of A into probability of B. So probability of A intersection B is equal to probability of A into probability of B. And this is an important relation. Indeed, this relation gives the necessary and sufficient condition for checking the independence of two events. That means two events A and B are independent if their joint probability is equal to the product of their individual probabilities. This result can be extended to more number of events, say 3 events, as follows. The events A, B and C are independent if and only if following 4 conditions are satisfied. Number 1, probability of A intersection B is equal to probability of A into probability of B. Then probability of A intersection C equal to PA into PC. Probability of B intersection C equal to probability of B into probability of C. And finally probability of A intersection B intersection C must be equal to probability of A into probability of B into probability of C. In general, it can be easily shown that for independence, in its statistical independence, for statistical independence of n events 2 to the power n minus of n plus 1, such conditions must be satisfied. Let us now take an example to clearly understand the notion of independence. Consider a random experiment of picking a card from a pack of cards. There are 52 cards in a fair pack of cards. Let us define two events. A is the event that the card picked is a jack, and say B is the event that the card picked is a club. The probability of A is there are 4 jacks in the pack of cards and there are total 52 cards, so the probability is 1 by 13. The probability of event B, there are 13 clubs and total 52 cards, so the probability is 1 by 4. Let us now look at the joint event A and B, A intersection B, which means a jack of club. Certainly there is just one such card in a pack of cards, so the probability is 1 by 52. Now 1 by 52 is equal to 1 by 13 into 1 by 4, which is same as 1 probability of A into probability of B. So from here probability of A intersection B is equal to probability of A into probability of B. Therefore, in this example, we see that the events A and B are statistically independent. This symbol we normally use to show the statistical independence. And finally, let us understand the difference between mutually exclusive events and the independent events. So mutually exclusive because many times students get confused between the exclusive and independent events. When we talk about exclusive events, there is a link between the two events we are talking about. For example, if A and B are mutually exclusive, then if A occurs, then B cannot occur, and if B occurs, A cannot occur. For example, if A denotes the even number and B denotes the odd number, so if A occurs, B cannot occur, and if B occurs, A cannot occur. That means A and B are mutually exclusive. So that means there is a link between the two events. There is no such link in case of independent events. That's why they are called independent. So no such link. Moreover, the disjoint events are defined over the same sample space. Whereas the independent events may be defined over the same sample space as in the example we just saw, or they even may have different sample spaces. For example, if we consider two different experiments, rolling a die and tossing a coin, and we talk about events of getting an even number on the die when the coin tossed shows up a heads. So there is no relation actually. So they are independent events. So in this module, we looked at three very important notions of joint, conditional, and independent events: the joint and conditional probabilities and their relation, and finally we distinguished between the mutually exclusive events and the independent events. So that's all for this module. Thank you.